Chapter 2, Theoretical Foundation of ZONAIR. ZONAIR solves the linear small disturbance potential equation, and for the subsonic flow, it solves this equation, and for supersonic flow, it solves this equation. For subsonic flow, this is a parabolic equation, and in supersonic flow, there's a hyperbolic equation, where phi is the perturbation velocity potential, and beta bar is the square root of 1 mass m squared. M is the free string Mach number. Then if we apply the Prandtl-Glauer transformation, and we can convert these two equations to a Laplace type of equation. This linear small disturbance potential equation is valid only for inviscid flow, attached flow, and when the thickness of the configuration is small, and is irrotational flow, and for inviscid flow, however, ZONAIR is equipped with a boundary layer option that used the inviscid solution to compute the skin friction due to boundary layer. And because it's attached flow, the flow is attached to the surface. Therefore, ZONAIR cannot predict separate flow. And when the thickness ratio of the configuration is small, this implies ZONAIR solution is not valid in transonic and hypersonic flow. Okay, so thickness times the Mach number must be very, very small. Because of the irrotational flow, the flow ahead of the blunt nose body is highly rotational at the supersonic Mach number, in which the ZONAIR solution is not valid. For blunt nose body in supersonic flow, ZONAIR is equipped with a correction scheme based on the exact Euler solution to correct the ZONAIR's potential flow solution. And this Laplace equation has an integral solution. So if we consider a volume V and enclosed by S1 and S2, S1 consists of surface of the configuration and the wake. For point P, the potential is equal to a surface integral, and where Vs we call it doublet, and partial V partial N we call it source singularity, and the N is the orthonormal vector of the surface, and the partial V partial N is N dot gradient, and the E is 2 pi for supersonic and 4 pi for subsonic. The R for subsonic flow is kind of a distance between x and x naught, y and y naught, z and z naught. However, for supersonic flow, this R represents a cone. So solution is only exists within the cone. So if the R goes to infinity and the velocity potential vanish, so the integral along S2 vanishes. So we only need to solve this integral equation on the configuration and on the wake surface. And we also have the wake condition. For three-dimensional flow, wakes are in general physically identifiable regions of rotation flow which carry away the vorticity generated within the boundary layer on the physical configuration surface. In the limit of infinite Reynolds number, the wake are infinitesimal thickness. Thus, the flow must be tangential to the wake surface. So the flow along the normal direction of the wake is 0. Therefore, we do not need to put source singularity on the wake. We only need to put doublet. And also, because the wake surface cannot sustain force, the pressure difference delta Cp between the lower and upper surface of the wake is 0. So because Cp is negative 2 times the partial phi partial x. Thus, the partial phi partial x on the lower surface and on the upper surface, the difference is constant. Okay, and so is 0, meaning the velocity potential on the upper surface minus on the lower surface minus the upper surface is constant. So in ZONAIR, the wake surface are modeled by 2 flat sheets. So surface extend to infinity, one attached to the trailing edge of the upper surface of the wing, another to the trailing edge of the lower surface of the wing. The potential phi on the upper surface is constant and equals that at the trailing edge of the upper surface. Likewise, the phi on the lower surface wake is equal to the potential at the lower surface trailing edge. So based on these 2 equations, and the wake equation can be represented by this integral. Then on the configuration, the phi and partial n represent 2 sheets of surface with an infinitesimal thickness distributed on the configuration surface with unknown strength called the singularity strength. We call it mu equal to phi is called the doublet singularity, and we call sigma is partial phi partial n is called the source singularity. The induced velocity component at the point P is the superposition of the influence from the source and the doublet singularities. So this is the perturbation velocity. This is due to source. This is due to doublet equal to the gradient of phi. Where phi s is the integral which has integrand 1 over r and take the gradient, and this is the unknown source singularity. The perturbation velocity due to doublet is n dot times gradient of 1 over r, and take the gradient with respect to x naught, y naught, z naught. So if we look at this integral, after we take a derivative, this becomes 1 over r cubed. But we have 2 integrals, so the resulting integral solution is in order of r. So it's not singular. So the source singularity solution is regular. However, if we look at the doublet integral, this after taking the gradient is 1 over r cubed, and take another gradient, the order is 1 over r fifth. But we only have 2 integrals, so the resulting VD is in order of 1 over r, and is singular at r equals 0. This singularity must be removed analytically. And then we can convert the doublet singularity to vortex singularity by using the Stokes theorem. And based on the Stokes theorem, a doublet distribution is equals a vortex singularity vector plus a ring of vortex. So gamma here is called surface vortex singularity vector. And so if you look at this integral, we only have 1 derivative, so it's 1 over cube, but we have 2 integrals. So the resulting integral solution is in order of r, it's regular. And this the line the line, the vortex line, and it has one derivative, so it's 1 over q, but we only have one integral, so the resulting solution is in the order of 1 over r. So this term still is singular. If the doublet strength between two adjacent panels is continuous, the effect of the line vortex vanishes because these two line vortex strength is the same. Then because the integral direction are opposite, so their effect are cancelled out. The remaining line vortex is along the wingtip, because at the wingtip there's no adjacent panel to cancel out this line vortex. But however, this line vortex is to simulate the vortex roll up along the wingtip in real flow. And the panel method discretizes the configuration into many small panels to approximate this equation 10, to approximate this equation. So we discretize. So this integral equation is summation of many panels, and then within each small panel we solve this integral analytically. And so within each panel, the distribution of a source and the doublet singularity is assumed to be a polynomial function. The Cauchy principle of the two singular integrals can be solved analytically, leaving the coefficient of the polynomial as unknowns. And so therefore, it is the order of the polynomial that defines the order of the panel method. The lower panel method uses the lower order polynomial, usually constant, and the high order panel use the high order polynomial, usually linear or quadratic. The high order panel method imposes the continuity condition in the doublet distribution by matching the polynomial coefficient on the adjacent panels among the common edges to eliminate the line vortex singularity. The lower order panel method do not impose this condition. The line vortex term along the common edge of the two adjacent panels cannot cancel with each other. The line vortex create a jump in doublet strength across the panel. The lower order panels such as NAR panel, Hayes curve, VSL, and USL, and SOSA do not work well for supersonic flow. And higher order panel method like a pan-air and ZONAIR can ensure the solution accuracy by for both subsonic and supersonic flows. And so if the doublet singularity is discontinuous among two adjacent panels, the jump in doublet strength due to the line vortex term along the common edge can create a superior velocity. This superior velocity travels not only outside the body but also inside the body. And in supersonic flow, this superior velocity inside the body decays inversely with distance, because the integral contains 1 over r. R is like distance, so usually do not cause a serious problem. This is the reason that the lower order panel method can work well for subsonic flow. In supersonic flow, the disturbance velocity does not vanish because 1 over r it represents r is a cone, and so because 1 over r equals 0 along the Mach wave. So its effect propagates in the downstream direction. Wherever this superior velocity hits inside the body surface, it creates an error at this location. This process accumulates errors that frequently serious enough to produce a totally incorrect flow solution. So, for example, this is a cone, seeing the cone case in Supersonic, and because the slope here is discontinuous, so that if you use the lower order particle, it will create a superior velocity along this edge, and this velocity bounce back and forth inside the body. The number of bouncing of the superior velocity increases rapidly inside the rear cone. The solution on the rear cone is totally unacceptable. This is the solution. The blue line is the exact analytical solution of the cone cylinder cone in supersonic flow, and the pan here and zone here are two high order particles shown by the red and blue squares. Then you can see that they compare well with the exact solution. But if you use the low order particle like US arrow, and you can see the solution on the rear cone, and it is totally incorrect. Then the boundary condition, for the boundary conditions, ZONAIR imposed the Newman boundary condition above the configuration. So it's so S equal to 0 plus to satisfy the flow tangential condition. So no flow can penetrate into the body. And also ZONAIR imposed the Dirichlet boundary condition beneath the configuration surface, so the velocity potential at the lower surface is constant. Okay, so this is the Newman boundary condition. This is the Dirichlet boundary condition, and we also have the Wick condition. And despite implementing inversive methods, ZONAIR attempts to model the real flow by assuming the thickness of the boundary layer to be infinitesimal. This infinitesimally thin boundary layer is modeled by source and the doublet sheet on the panel. Above this thin boundary layer, the flow is tangential to the boundary layer. Beneath it, the flow velocity is 0 to simulate the no-slip boundary condition. Because phi on the lower surface is constant, so if you take a gradient of phi, the velocity are zeros. With the two sets of boundary conditions and the two sets of unknown, singularity, the source, and the doublet can be solved. And ZONAIR use the transpiration boundary condition. So ZONAIR does not physically rotate the model to account for the angle attack or control surface deflections. ZONAIR always solve the integral equation of the linear small disturbance potential equation on the user input panel model. The surface of this panel model is called S0. And the effect of angle attack, seismic angle, control surface, the deflection, roll rate, pitch rate, yaw rate are incorporated on the boundary condition. This technique is called transpiration boundary condition. So this is the Newman boundary condition. So we take the n is the odd normal vector of the panel model, which is input by the user, which does not contain the angle attack and control surface deflection and so on. And this normal vector dot, the gradient of phi, is the velocity along the normal direction applied above the surface, equals the negative n. N is the normal vector of the panel, including the control surface deflection, and V infinity can be expressed by this alpha and beta, okay, angle attack and the side slip angle along the IHK direction. Omega cross R is the induced velocity due to the roll rate, pitch rate, and yaw rate. Okay, and so the n now is all normal on S now, and n are the all normal of the configuration, at the beta and alpha and beta, including control surface deflection. So the control surface deflection is incorporated in the in this normal vector. And ZONAIR assigns an unknown doublet singularity strength, we call it mu. Mu goes to 1 to ng, where ng is the number of grid point. At each grid point, a linear doublet distribution is distributed over the panel that share the same grid. So those panels share the same grid, and the superposition of the linear doublet distribution at all grid points is the continuous doublet distribution, but the slope is not continuous over the conversion, so that the line vortex integral need not to be evaluated. The control surface for solving the doublet singularity strength are located beneath all the grid point, and Dirichlet boundary condition is imposed at those grid point. And ZONAIR assign unknown constant source singularity on NP number of panels, and the source singularity is not continuous over the conversion, because the source singularity cannot be continuous over a sharp corner. Control point for solving the source singularity strength are located at the centroid of each panel, where the Newman boundary condition is imposed. After the line vortex is eliminated by the continuous doublet singularity over the configuration, the remaining singularity are the line, the linear doublet or constant vortex singularity vector on the configuration, and also the wake surface shading from the trailing edge and extend to infinity. And we have a line vortex singularity along the wingtip due to the absence of a adjacent panel along the wingtip. And the wake surface can be eliminated by assuming it is a flat sheet of surface from the trailing edge to infinity. And for a grid point with a doublet strength mu at the trailing edge of the wing, the doublet distribution on the wake is constant, also is mu, and along the streamwise direction, as is linear along the spanwise direction. Because the integral equation of the wake surface can be solved analytically, so we integrate from the wing trailing edge to infinity, and because this integral has can be solved analytically, therefore the wake surface is modeled by a line wake segment along the trailing edge with the width of delta y, and the wake surface model is not required. Greatly simplify the panel modeling effort because so if you along the wing trailing edge, and when you only need to specify a wake segment. This wake segment is specified by C-bar, and you don't need to worry about the wake surface, because internally ZONAIR will sweep this line segment to infinity and solve this integral analytically. At the end, you only need to once you solve the mu at the trailing edge of the grid, then the wake influence effect can be taken into account. And then we can construct so-called aerodynamic influence coefficient matrix with unknown doublet singularity strength at the grid point and the source singularity strength on panel. If we have ng number of grid points, and we can establish ng equations by imposing the Dirichlet boundary condition at the control point for the doublet singularity. So if we have a point at the control point and evaluate beneath the surface, and we have a summation from 1 to ng and 1 to np. Ng is the number of grid point, np is the number of panels, and this is the unknown doublet, this is the unknown source. A and B is the integral solution of those two integrals. Then we can establish NP equations by imposing the Newman boundary condition at the control point for the source singularity. So we impose the Newman boundary condition at the center of each panel, and that equal to mu times c and sigma times d, and equals to this friction velocity along the normal vector, and this is due to the pitch rate, yaw rate, and roll rate, and where C and D are the integral solution of those two integrals. And all those integrals can be solved analytically. Therefore, we can establish Ng plus Np equation, which leads to the matrix equation shown as here. Then if we invert this matrix, and then we can solve for the unknown doublet and the sigma. So the inverse of this matrix is called AIC. So okay, so if you look at this AIC matrix, because the integral is evaluated on the S naught, which is the panel model, and therefore, as long as the panel model is not changed, and you can reuse the AIC matrix to calculate to obtain the flow solution and other flow condition. For example, you have a different angle attack, different control surface diffraction. You don't have to recompute the AIC. You can reuse the AIC. So the most computed time of panel method is in computing the AIC matrix. However, since the AIC is independent of the boundary condition, the angle attack, size angle, pitch rate, roll rate, pitch rate, yaw rate, and the control surface diffraction, it can be saved and reused for other boundary conditions. Thus, once AIC is obtained, it takes only a little computational time to solve the flow solution for other boundary conditions. So in contrast, whenever the boundary condition is changed, the CD must be re-executed. AIC must be recomputed if the Mach numbers change, the panel model is changed. And AIC also can be used to perform static aeroelastic analysis. Another modeling technique in ZONAIR is called thin wing modeling. Because the integral equation of a panel method contains 1/turn, the AIC matrix becomes singular when the distance between two panels approaches 0. This indicates that for a very thin wing, the AIC is ill-conditioned unless a very refined panel model is used. And this problem can be circumvented by the thin wing modeling technique. That treats the wing as a flat sheet of surface with an infinitesimal thickness. So considering the integral equation of a 2D foil, and so we integrate along the surface and along the wake. However, if T approaches 0, this integral equation can be approximated by taking the limit, and this the difference of the doublet, this the difference of the source, and then this we call the difference between the difference of doublet strength between the lower surface and upper surface, and so this represents a double sheet on the flat surface to simulate the tangential flow jump across the wing, And the difference in the source strength can be represented by the slope of the airfoil thickness to represent a source sheet on the flat surface to simulate the flow thickness effect. So if you have a wing on the angle of attack, first we put a source there, and so based on the source strength, we can simulate the thickness effect of the wing, and then we will use the vortex singularity based on the angle of attack to generate the lift. The doublet sheet on the 3D wing is clockwise continuous but spinwise discontinuous. The two line vortex are generated along the two side edge of each strip on the wing. The wing modeling is not required. The wake modeling is not required because the wake effects are included in the vortex integral equation. This we're going to talk about in detail later. And once we have the perturbation velocity based on Bernoulli equation and isentropic assumption, we can calculate the CP, and gamma is a specific heat ratio. However, CP must be within the physical limit of the stagnation pressure and the vacuum pressure. If the CP exists this limit, a warning message is printed on the output file that implies the panel modeling is not healthy. And we can also calculate the local Mach number, and then we can integrate the CP to get force along XYZ and moment along XYZ. But this force and moment are in so-called wing axis. And then we have to calculate the lift, side force coefficients, drags, roll moment coefficients, pitch moment coefficients, and yawing moment coefficients, and in the body axis. Okay, where C here is the reference core, B is the reference span, S is the reference area. That's the end of section